I'd like to cover three subjects. What I'll call the standard model of comets, which has many of the advantages and disadvantages, the standard model of particle physics, discussion of Planet X, and finally a brief discussion of Oumuamua, the first interstellar asteroid. Okay, so the standard model of comets is good. It's not perfect, but like the standard model of particle physics, it almost certainly contains a great deal of the truth and provides a very elegant explanation of much of what we know. In the case of Planet X, okay, I'll do it this way. In the case of Planet X, things are much less clear. We have a number of good theories, but it's still unclear how things are eventually going to work out. And in the case of Oumuamua, we have absolutely no idea what's going on. So for the purposes of this talk, comets are chunks of ice and rock a few kilometers across. We have half a dozen cases where they've been visited by spacecraft, so we have direct images. The typical densities are less than unity, which suggests that they're made of ice and have large voids in front of them, giving rise to the idea that they're rubble piles. Typical mass is a few times 10 to the 16th grams. And what we believe and what I'll assume is that comets are leftover small bodies or planetesimals from the assembly of the planets. The reason that comets are visible is because they're made of ice and volatile material. When they come close enough to the sun, they develop an atmosphere and a coma, which can become a coma and a tail, which can become quite bright. In actual fact, they have two tails, which are separated here, a plasma tail and a dust tail. For our purposes, the important fact is that these tails only develop when the comet is close to the sun. At large distances, the nucleus, the solid body of the comet, is visible only by reflected sunlight, and that means that at large distances, the brightness falls off like 1 over r to the fourth, r squared for the light to get there from the sun and r squared for it to come back. What that means is that it's very hard to discover comets that are more than a few astronomical units away from the sun. And that in turn means that once the comet comes close enough to the sun to be seen, it will be heated by the solar radiation, lose its volatiles, and it typically can't survive more than at most a few hundred orbits. And the inevitable conclusion from that is that you need a reservoir for the comets. The lifetime of the comets, once we see them, is very short compared to the age of the solar system. So you need a reservoir that satisfies two contradictory requirements. On the one hand, it has to be stable enough to store comets on gigayear timescales, but on the second part, it has to be sufficiently leaky that comets are continually leaving the reservoir and coming into the area of visible space where we can discover them. And the search for reservoirs that satisfy those two conditions is much of the story of trying to understand the origin of comets. To start, let me just remind you of what we'll need from Kepler mechanics. Of course, we're going to specify the orbits by the semi-major axis and by the eccentricity. The point of closest approach to the sun, or the perihelion, is just semi-major axis times 1 minus the eccentricity. The inclination of the orbit I'll always measure relative to the ecliptic, to the plane of the planets. And Kepler's law then says that the orbital period in years squared is the cube of the semi-major axis in astronomical units. So if the semi-major axis is 10 to the fourth astronomical units, the period's 10 to the 6 years. The energy per unit mass in the standard Kepler formula is like that, and following the tradition of particle physics, I'll define dimensionless units in which g is 1, the solar mass is 1, 2 is 1, and minus 1 is 1. And so I'll just use 1 over the semi-major axis to specify the energy. So this is a plot of all of the comets in a database provided by JPL. This axis is the inclination of the comet orbit. This axis is the period of the comet. I've taken it up to 10 to the 5th years and stopped there. That's because When the orbit is very long, it's nearly parabolic, and it's quite hard to distinguish exactly what the orbital period is. So I've just taken all the near parabolic orbits and plotted them there. And the most striking feature is a clear distinction where if the comet orbital period is less than about 20 years, the inclination is quite low, typically around 10 or 20 degrees. And if the orbital period is longer than that, the inclination is relatively isotropic. Just for reference, there's Halley's comet. Since there's nothing there's no dissipative agent acting on the cometary orbit, the conclusion, you can't concentrate orbits close to the plane of the planets. And so the inevitable conclusion is that the comets in this clump had to have come from a reservoir which also is flat, which has low inclination relative to the plane of the planets. That the existence of such a reservoir was predicted in the 1980s, and in the early 1990s, Jewett and Liu discovered the first object in what's now known as the Kuiper belt, a belt of small bodies, including comets and objects up to a few hundred kilometers in size that orbits outside Neptune at 30 astronomical units out to about 50 astronomical units. So we now believe that the Kuiper belt is the reservoir which produces all of these planets. We have something like 2,000 objects in the Kuiper belt now with well-determined orbits. The Large Synoptic Survey Telescope, which should be operating in the next few years, will discover somewhere between 50,000 and 100,000 more. The total mass is about a tenth of an Earth masses. What's a little less clear is what causes the leakiness of the Kuiper belt. It's probably some combination of collisions between comets that jostle the orbits and send them onto new orbits that come close to the sun, or very weak long-term orbital instabilities. That's pretty much all I'll say about the Kuiper belt for now, but I just wanted to point out that as of January 1st, we can add an image of a Kuiper belt object to the images of other cometary objects. It's somewhat larger, not surprising since it was only discovered because it was large enough to be seen with ground-based telescopes. And what strikes me as remarkable is the number of objects that show this bilobe dumbbell-shaped structure. The Kuiper belt object, Halley's comet, Comet Borrelly, the Churyumov-Gerasimenko, the comet that the European Rosetta mission went to, Hartley 2, and why this structure is so common, I think, is still something that's not well understood. But it does encourage us to, because it's consistent with the idea that Kuiper belt objects and comets are really the same population. Okay, so let me move on to the comets with periods outside 20 with periods longer than 20 years in this region. As I say, their orbital distribution is nearly isotropic. As I also said, it's a problem exploring the distribution of orbits out here, because as the orbit becomes nearly parabolic, the period goes to infinity. So it's better to deal with 1 over semi-major axis rather than the period. The other thing that's crucial for understanding what happens is to recognize that when we see the comets, they've already come through the outer solar system past Jupiter and Saturn. Jupiter and Saturn have changed their orbits, changed their energy, changed their semi-major axis. The typical energy change is about 10 to the minus 3 inverse astronomical units. And in order to understand where they came from, you don't want to be confused by these changes. So what you have to do is numerically integrate the orbits from where you see them now back out until they're past Neptune, say out at 40 or 50 astronomical units, and measure the inclination and eccentricity and semi-major axis out there before they encountered the planets. And that energy is, called the original energy. That is the energy the comet had before it entered the planetary system. This is what a plot of the original energies looks like. So this is the 1 over the original semi-major axis in units of 10 to the 6th astronomical units. So this is 1,000 AU, 2,000, 10,000, and parabolic orbits here. My first comment on this remarkable plot is that if you look in detail at everything out here, everything with negative semi-major axis, those are on hyperbolic orbits. Those are all have error bars, either due to observational errors or non-gravitational forces and outgassing that make them consistent with parabolic. And so it's reasonable to assume that there are no hyperbolic orbits. We haven't seen any comets come in on hyperbolic orbits. That in turn means that most of the comets that we're seeing coming from large orbital periods are coming from a limited range of semi-major axis somewhere outside of 10,000 astronomical units. And that leads to the conclusion that the reservoir for these comets is distinct from the Kuiper belt. It's a roughly spherical cloud of comets at a distance of something like 30,000 astronomical units from the sun. This is a remarkably large distance in the sense that the distance to the nearest star is about 270,000 astronomical units. So although the Oort cloud is associated with the solar system, it goes out to halfway to Alpha Centauri. Everything in this dramatic spike here is a member of the Oort cloud. I'd just like to stress from the physics point of view how remarkable this result is. And there are a couple of ways to persuade you that it's remarkable. The first is that if we neglected the gravitational perturbations from the planet, all of the comets from within this cloud would pass through 1 astronomical unit where we see them with a speed that's 42 plus decimals kilometers per second with a spread of 50 centimeters a second. So to roughly 1 part in 10 to the 4th, they're all on orbits with exactly the same energy. Another way to phrase it is to imagine that the gravitational force wasn't pure 1 over r squared, that suppose gravity was described by a Yukawa potential, that is that the graviton had some finite mass, then the finite mass of the graviton would weaken the potential at large distances. That means that comets out here, which we assume are bound because we're assuming a 1 over r squared force, would no longer be bound. And since it's improbable that there would be a huge cloud of unbound comets with precisely this energy, by demanding that they're bound, we can set a limit on the mass of the graviton, which is about 3 times 10 to the minus 23 electron volts. For comparison, we got another limit from the neutron star merger observed by LIGO from the simultaneity of the arrival of the signal from gravitational waves and photons. Obviously, that's a different process. Nevertheless, I feel I should point out that the limit is weaker than the limit we can get from the comets. The other remarkable feature of the Oort cloud I wanted to point out is that this is the original data that was used by Oort to make all these deductions. You can see he had 10 comets in the spike and about another 10 outside it, and I'm just putting this up as a reminder that in these days of big data, sometimes you can reach interesting conclusions with very small data. Okay, the other thing, the other deduction which you can make and which Oort made is that since the typical kick in energy that you get when you pass through the planetary system is something like 10 to the minus 3 or this large on this scale, it means that once you see a comet coming from the Oort cloud, it'll never go back to the Oort cloud. It will either get a kick of energy that almost certainly makes it unbound or a kick that makes it much more bound. And if it becomes unbound, it's lost from the solar system forever. If it becomes more bound, it starts to undergo a random walk. Every time it comes back to the planetary system, it gets a positive or a negative kick. And so just like in the classic Gambler's Ruin problem, the fraction of new comets that survive for n orbits in the solar system goes like n to the minus a half. So that means that these comets are almost certainly comets that were once in the Oort cloud and have undergone a random walk down to these more bound energies. In order to fit this quantitatively, you need to make the plausible, I think, but still somewhat arbitrary assumption that the comets that have been stored in the Oort cloud for a long time have more volatiles than comets that have gone past the sun, close to the sun multiple times. That means that they fade as they return to the sun. If you put in an empirical fading law that says that the probability that you'll still be visible after n perihelion passages goes like n to the minus 0.6, then you can reproduce this distribution very well. Well, you can still do more with this very simple set of data. The Oort cloud is at sufficiently large distances that kicks from passing stars in the galactic tide are sufficient to randomize the orbits of stars in the cloud. And the best way to think of that is to imagine that you have a phase space, and for comets at a particular semi-major axis or energy, they have an energy surface in phase space, and the kicks from the stars in the tide tend to uniformly distribute them around that energy surface so that you have a very close analog of the microcanonical ensemble. If you have a uniform distribution over the energy surface in a Keplerian potential, it's straightforward to show that the fraction of comets that have a perihelion less than some value is just the ratio of the perihelion to the semi-major axis. That says that the number of comets inside some perihelion distance should rise linearly with perihelion. There's the data for the comets from the Oort cloud, and you see that they're following that very precisely out to about 6 astronomical units, at which point the discovery rate starts to fall off because they become too faint to discover. Also, if you're uniform on the energy surface, you should be isotropically distributed, and so the fraction of comets with an inclination less than some value should be linear in the cosine of the inclination. That's the distribution of the inclinations, which is, again, very closely consistent with uniform distribution on the energy surface. Well, you can, again, do more with these arguments. And again, all these arguments are due to Oort. We know that the rate of arrival of comets from the Oort cloud inside 1 astronomical unit is about 1 per year. We know the orbital period at 30,000 astronomical units. From Kepler's law, it's about 5 million years. We know that the fraction of comets with perihelion less than some value is given by the ratio of the perihelion to the semi-major axis. We know that they're uniformly distributed on the energy surface, and that says that the number of comets in the Oort cloud is the number that come by per year times the orbital period times the fraction of the phase space that we can see them in. So 1 per year, 5 mega years, the ratio of 2 times 1 astronomical unit to 30,000 astronomical units gives you 10 to the 11th comets. And with a fractional typical comet mass of around this value, you get a total Oort cloud mass of 1 Earth mass.
Scott, when Oort did it, how big was his error bar on the total mass?
Well, we don't even know now how big his error bar is how big the error bar is in the total mass. But I do want to point out that, from his population of 10, he extrapolated by a factor of 10 to the 10th, and as far as we know, that answer's right within a factor of 2. Okay. No, but he knew the rate at which the stars should isotropize things, and so he was able to make a plausible calculation showing that it should be. Okay, well, we're not done yet. This is a picture not of the comet cloud, but of the nuclear star cluster surrounding a black hole. So this is center of a typical galaxy. There's a black hole here. It's surrounded by a star cluster in which this is a typical star. If the star passes too close to the black hole, it's tidally disrupted by the black hole. and that means that it's lost from the star cluster. That means for every star, if you look at the distribution of velocities, there's a cone in velocity space such that anything whose velocity is inside this cone is going to have a perihelion distance smaller than the disruption radius and is going to be lost from the star cluster at the next encounter. Now, the reason I brought this up is that it's a direct analog to what happens from the Oort cloud. In this case, the loss is not because of tidal disruption from the sun, but because the gravitational perturbations from the planets are strong enough to remove it from the Oort cloud, either into a more tightly bound orbit or an escape orbit. Roughly speaking, any comet that has a perihelion passage less than about 15 astronomical units between Saturn and Uranus is going to be lost from the Oort cloud. So you can analogously define a loss cone, that is a cone in velocity space in which the perpendicular velocity is sufficiently small that the comet will be lost from the Oort cloud at its next paracenter. The reason that this is important is that we're sitting in the middle of the loss cone. The geometry is something like this. If we're, say, sitting on the star and looking towards the sun, here's the loss cone, radius of 15 astronomical units in perihelion distance. We only see the comets typically if they come within about 2 or 3 astronomical units. The comet is undergoing a random walk around the energy surface due to passing stars. If the typical step caused in the random walk in velocity space is small compared to the size of the loss cone, the comets will sort of diffuse into the edge of the loss cone and be lost before we ever see them. That means that the only comets we can see are ones where the kick per orbit due to passing stars is sufficiently large to take them from outside the loss cone to inside, to very close to the sun, where we can see them in less than 1 orbit. Well, we can calculate what that requirement is. The typical change in perihelion distance is a very strong function of the semi-major axis. As the semi-major axis increases the lever arm, and so the torques become bigger, and the orbital period gets longer, so you have longer time to change the angular momentum. So all you do is you take this number, which you can normalize from the properties of stars in the solar neighborhood, calculate at what semi-major axis it's big enough to move comets from 15 AU to 0 in 1 orbital period, and you conclude that this case, the full loss cone, requires a semi-major axis of 35,000 astronomical units. You'll recall that that's exactly the semi-major axis at which you see the Oort cloud, and so the conclusion is that you can predict the size of the observed Oort cloud with no free parameters. There are other consequences. Since we've successfully done that, it also says that comets from smaller semi-major axes we're never going to see. They'll be in this limit where they'll get removed from the Oort cloud before we see them. And so it says that the Oort cloud might extend to much smaller radii and have many more planets, many more comets and more mass than we think. So far, I think this has been, we've been able to provide a pretty good description of the current properties of the Oort cloud. We haven't said anything about its origin, but in fact, this is one of the few cases in astronomy where you do have a pretty good origin story. You assume that we have at an early stage of the solar system, the giant planets are fully formed in their current orbits, or maybe you allow for migration of Uranus and Neptune according to models like the Nice model that include migration in the first 100 million years of the solar system. Then you say that after the planets had formed, there's a set of leftover test particles or planetesimals or comets on nearly circular coplanar orbits in the disk of the solar system. You allow for the effects of the galactic tide and perturbations from passing stars. And basically the process is that gravitational perturbations from the planets acting on the planetesimals gradually excite the eccentricities. The comets random walk out to larger and larger orbits until the galactic tide or the perturbations from passing stars change the angular momentum so much they no longer return to the planetary system. and then they're frozen in place, or at least their energy is frozen in place until they happen to return to the planetary system. The nice thing about all this is that it's just a matter of calculating orbits, and so all you do is set up these initial conditions and follow the test particles for 4.5 billion years, and the only, apart from modest uncertainties in the initial conditions, you're just doing an n-body problem. So this is what happens when you carry out the n-body problem. So this is a plot of the eccentricity of the surviving test particles against the semi-major axis. This is a set of particles whose eccentricities go up with semi-major axis in such a way that the perihelion is still inside the planetary system. This is basically the pipeline of comets that are random walking their way out to the Oort cloud. So basically their perihelion is relatively fixed. They random walk in semi-major axis, and then at this point the torques become strong enough that the eccentricity goes down. They no longer feel the planets, and then they just wander around here for the rest of the 5 billion years.
How do you model the eccentricity excitation?
You put down a set of the 4 giant planets. You calculate the orbits. This is a plot of the inclinations relative to the ecliptic. You can see that in the pipeline or the scattered disk, the inclinations stay relatively low, and then once the external perturbations become strong enough, you build up a more or less isotropic distribution of inclinations. So the conclusions from this is that the part of the Oort cloud that we see is outside about 20,000 AU. That's the outer cloud. There's an inner cloud as well that stretches into about 2,000 astronomical units. The outer edge of the cloud goes out to 100,000. There is a small fraction of the comets on a scattered disk, and the distribution is relatively spherical. One of the reasons it's spherical is just the coincidental fact that the galactic plane and the ecliptic plane are inclined by about 60 degrees. If they were nearly aligned, the whole distribution in the Oort cloud would be quite different. The fraction that are surviving looks something like this. The population of the total Oort cloud grows to about 1 giga-year, and now is gradually being whittled down by passing stars that are kicking things onto escape orbits. Here's the inner cloud and the outer cloud. You can see that at the present time, the populations of the two are about the same. The efficiency is about 2.5%. That is about 2.5% of the planetesimals left over in the protoplanetary disk are still in the outer cloud. And for reasonable models of the protoplanetary disk, given that efficiency, you can calculate what the mass of the outer Oort cloud should be. It turns out to be about 1 Earth mass, which of course is exactly the same within the errors as we got from the phase space arguments. So in that sense, things hold together rather well. One of the things that we'll learn more in the near future is more about the inner Oort cloud. This is a plot of the distribution of comets coming into the inner solar system as a function of perihelion distance. At the moment, we're looking, we're limited to seeing things out to about 5 astronomical units. So almost everything that we see is coming from the outer Oort cloud. But with LSST, we'll get a survey of a significant fraction of the sky, which is far more sensitive. We'll be able to move out in rare cases to 15 or 20 astronomical units. Then we'll be dominated by things coming in from the inner Oort cloud, and we'll get the first real test of whether the actual population of the inner cloud is consistent with the formation model. Despite the success of this model, it leaves a number of things out. Leaves out the fact that the sun probably formed in a dense star cluster. It might have exchanged comets with other stars in the cluster. Leaves out the fact that we don't really know how much the planetary orbits have migrated. We don't really know how much the sun has migrated in the galactic disk, and so how typical the environment in the solar neighborhood is. And we don't know whether other massive bodies might have been present in the protoplanetary disk that were later on ejected in the same way that the comets were. That last concern leads me to the second topic, which is Planet X. One of the significant problems with the standard model of the Oort cloud is that it doesn't explain the properties of Sedna and some of its companions. So Sedna was discovered by Mike Brown at Caltech. It's about 500 kilometers radius. It has an aphelion of almost 1,000 astronomical units and a perihelion of 76 astronomical units and a low inclination. Now, the whole idea behind the standard model for the formation of comets has always been that all the comets formed in the protoplanetary disk in the region of the giant planets. But Sedna has a perihelion that's so large that it's not influenced by any of the giant planets. In particular, if you integrate its orbit forward or back 5 times 10 to the 9th years, it basically sits in exactly the same orbit. It never interacts with the planets, so how did it get there? You might argue that, well, you shouldn't spend too much time worrying about a single body, but there's now something like 30 other examples with similar orbits, a population that's come to be called the detached disk. And so the question is, how did Sedna get there, and how did the other members of the detached disk get there? There are a variety of theories, but I want to focus on one I alluded to before. The standard model basically has two kinds of particles in it. It has planets, which are quite massive. It has test particles that have no mass. That's almost certainly oversimplified in the standard models of planet formation. Since the planets are built up by accumulating planetesimals, it's inevitable that there are, or should at one point have been, bodies of intermediate mass. The cores of the giant planets are maybe 10 Earth masses, and so there should have been a much larger number at various times of things between, say, 1 Earth mass and 1/10 of an Earth mass. And as far as Jupiter's concerned, it doesn't care whether something's a test particle or 1 Earth mass. It's going to eject it in exactly the same way. And so these other bodies would have been subject to exactly the same evolution as the comets. So one consequence of that is that there could easily be 1 or more bodies that are Mars-sized or Earth-sized in the Oort cloud. Those are essentially impossible to detect with current technology. But a more interesting possibility is that as these bodies were random walking in the scattered disk, they have sufficient mass that they would exert torques on the comets that are on their way, or in the scattered disk as well. And because those bodies are on relatively small orbits, they're far more effective than the torques from the galactic tide or passing stars. They can they can change the perihelion distance of the other comets on a time scale short compared to the revolution, lift their perihelion distances away from outside Neptune's orbit and freeze them in place, in much as what you see with Sedna. You can do simulations of this process, and the simulations show that it will create a sort of thickened disk or a mini Oort cloud that contains comets, but might also contain 1 or 2 of these residual planets at distances of a few hundred astronomical units. These are quantitative calculations done by Kedron Silsby, who's a graduate student at Princeton. You'd simply lay down the giant planets plus a set of extra bodies of range of masses and just integrate the orbits for 4.5 billion years. These are the samples of the surviving bodies. You can see the semi-major axis of the survivors are somewhere between 50 and a couple of hundred astronomical units, perihelion between 40 and 100 astronomical units, inclinations of maybe 20 plus or minus 10 degrees. Now, if these bodies didn't have mass, they wouldn't have survived. They would have evolved into the Oort cloud or have been ejected. It's only because masses were present that this structure forms, And the general properties of the structure, the typical inclination, semi-major axis distribution, and perihelion distribution are exactly the same as what you see in the detached disk, of course, with pretty big uncertainties. So this provides an extremely natural mechanism for making the detached disk, which we observe. But in addition, in about half the simulations, one or two of the most massive bodies with masses between Mars and Earth survive in the detached disk as well. So we conclude that it's likely that, but far from certain, that the solar system does have an extraplanet with a mass somewhat less than an Earth mass and a semi-major axis of a couple of hundred astronomical units. Now, I have to stress that this is not the planet X you've been hearing about in the media. This planet, the other planet X, is based on the observation that if you take a carefully selected sample of Kuiper belt objects with eccentric orbits and large semi-major axes, the lines of apsides, the long axes of the orbits, are correlated. They seem to be clustered in one quadrant of the sky. You wouldn't expect that normally because precession due to the giant planets ought to isotropize the orbits. And Batygin and Brown in particular have argued strongly that the only way to explain this is the presence of an extraplanet. The mass of the planet has varied between about 20 Earth masses and 5 to 10 Earth masses, and the semi-major axis is around 500 to 1,000 astronomical units. There are possible concerns with this argument. I worry that the clustering could be a statistical artifact because there's a relatively small number of objects, and the effect was discovered after they had made cuts on semi-major axis and other properties. There's a continuing concern that the clustering could in part be an artifact of observational selection procedures. Surveys always avoid the galactic plane because of the backgrounds. Most searches are from the northern hemisphere, and so forth and so on. Brown and Batygin claim that they have checked that, and that's not the explanation, but I haven't tried to confirm that myself. And finally, a planet like this, we just don't have any good way of forming it for any reasonable story about the formation of the solar system. So I feel I should give you, before leaving the subject, I should give you a scorecard on Planet X. I'll start the numbering with 9 for obvious reasons. The original Planet X was a body that was supposed to cause unexplained anomalies in the orbits of Uranus and Neptune. That led, of course, as we all know, to the discovery of Pluto, but it was rapidly discovered. Turned out that Pluto's mass was too small by a factor of more than 1,000 to produce the claimed anomalies. After Voyager flew past Neptune, they discovered that the standard value for the mass of Neptune was off by 0.5%. Once you made that change, almost all of the anomalies went away. And so it's pretty clear that there are no significant inconsistencies in the current ephemerides of the outer planets, and even if there were, Pluto is too small to cause them. This was, of course, the reason Pluto was demoted. I feel I should point out that the demotion started in New York when the new Hayden Planetarium opened and didn't include Pluto as its list of planets, and with its usual perceptive investigative reporting, the New York Times discovered this and publicized it. They had another article with the headline, "New York's a tough town for a small planet." And that's why Pluto's not a planet anymore. Second possibility is the Batygin-Brown planet, something that causes asymmetries in the distribution of outer Kuiper belt objects. Third possibility, Planet 11, is a massive body that was ejected into the Oort cloud along with the comets. We've also discussed Planet 12, something that's a member of the detached disk. Volk and Malhotra have pointed out that the mean plane of the outer Kuiper belt is slightly warped, and the most plausible explanation for that warp is the gravitational force from an outer planet. You can only get crude constraints on the combination of the mass and semi-major axis, but roughly speaking, the body that Volk and Malhotra argue for is consistent with planets 10 or 12. The observational constraints come from a variety of sources. If you're looking for giant planets, it's much easier because they're self-luminous in the infrared, so the flux only falls off like the square of the distance. On the other hand, terrestrial planets use reflected light, so the flux falls off like distance to the fourth. And since the flux is going like distance to the minus fourth, and the number of background stars goes like flux to the 3/2, if you want to try to double the distance you're sensitive to, you're going to see a factor of 2 to the 6th more background stars. So it's very hard. The WISE survey has ruled out any Jupiter analog within 80,000 astronomical units. So the Oort cloud doesn't have a Jupiter in it and probably doesn't have a Saturn in it. One of the most promising avenues for future searches are CMB searches. Basically, you just take something like, for example, the Planck maps, and you look for something that's moving back and forth with an extremely large parallax. If you assume a distance, then the parallax is determined, so there's no free parameters, and then you just march out in distance looking for sources that are wobbling in the required way. Once you've got a candidate, it's easy to do an optical search for the planet. The best current surveys are these two. They have reasonable sky coverage, mostly in the ecliptic, down to about the brightness of Sedna. Obviously, LSST will do better, but it's not covering the whole sky and even has difficulty covering the whole ecliptic. There are dynamical constraints. Fits to solar system ephemerides, as I've said, don't show any positive evidence for extraplanets, but are sensitive enough they could certainly detect some of the planets I've discussed in some phases of their orbits. Pulsar timing is becoming more and more powerful because arrays like nanograv that are searching for gravitational wave background have now found that one of the limiting factors in their sensitivity is uncertainties in the solar system ephemeris, and so they are gradually turning into combined searches for gravitational waves and better ephemerides in Planet X. And finally, there's the possibility that the planet can be discovered by gravitational lensing of stars in the Gaia catalog. As the planet moves along, it will cause a moving distortion in the positions of stars that could be detectable once we have the full Gaia data release. And this is just showing the current constraints on a simple plot of mass versus distance. There's the Kuiper belt objects. Those are limits from pulsar timing, from ephemerides, potential limit from Gaia, and a couple of the candidates, which you can see are not yet ruled out, but close enough to be interesting. Okay, for the last topic, I'm just going to give a brief review of Oumuamua. Oumuamua is a small body that was discovered by the Pan-STARRS survey. It's unique because it has an orbital eccentricity of 1.2. It's clearly hyperbolic at very high significance and is thus the first detected smaller body, the first detected solid body other than dust from interstellar space. It passed through perihelion. In September 2017, it was discovered post-perihelion. About a month later, its closest approach to Earth was 0.16, and there's only a limited observational arc because the last time it could be seen was January, so they only have a couple of months of observations. It's a point source. It shows no evidence of coma. There's no evidence of any gas from looking at for absorption lines in background stars. The conclusion from that is that it's an asteroid, that is, it's rocky rather than being a comet, which would be icy and should have exhibited some coma or emission. The colors are consistent with at least Oumuamua's here. It's consistent with at least some asteroids. It has a light curve. Rotation period is a little under 8 hours. The photometry suggests that the average radius is about 50 meters, and the amplitude of the light curve is a factor of something like 6 to 10. You can extrapolate its velocity back until before it encountered the solar system. That velocity doesn't match any nearby star. So, for example, I've argued already that comet cloud extends a significant fraction of the way to Alpha Centauri, but its velocity definitely doesn't match Alpha Centauri, so it's not an Alpha Centauri comet. On the other hand, its velocity outside the solar system is close to the velocity of the local standard of rest, which suggests that it's really, again, suggests that it's been coming from interstellar space. Okay, so those are the facts. Here are the puzzles. You can do the Pan-STARRS people have done a careful estimate of the sensitivity of the Pan-STARRS survey volume and duration, and have concluded that the discovery of one Oumuamua tells you with some uncertainty that the interstellar density is about 0.2 per cubic astronomical unit, which requires about 4 times 10 to the 16th per typical star. Let me remind you that the number of comets in the Oort cloud is 10 to the 11th, so you really need an awful lot of these. In terms of mass, if you assume that every star in the solar neighborhood produces Oumuamuas at the same rate, at the density of the object is 3 grams per cubic centimeter, as you would expect for a rocky asteroid, then every star has to produce about 40 Earth masses.
The dynamical heating of these bodies after they get ejected from stars?
Let me come back to that in a second. So for comparison, the original the protoplanetesimal solid mass in the solar system was maybe 50 to 100 Earth masses. That doesn't look so bad, except that, first of all, the size distribution of planetesimals means that most of the mass is in the most massive bodies. Oumuamua is much less massive than typical comets, so the total mass has to be a lot bigger. Second, only about 10% of stars have giant planets massive enough to eject small bodies, so I would say it's maybe not impossible, but very difficult to find enough solid mass to make enough of these bodies. Puzzle number 2 is that, as we've indicated already, comets are far more visible than rocky bodies because of their comas and their tails. If the first interstellar object is rocky and not icy, you can conclude that the fraction of icy versus rocky bodies of the same size has to be less than about 0.1%. On the other hand, in standard models of planet formation, rocky bodies are much less likely to be ejected than icy ones. There's more matter outside the ice lines. Outside the ice line, the escape speeds from the planets are larger, and so it's easier for them to eject things. The escape speeds from the system are lower, so it's a real puzzle why it doesn't show a coma or a tail. The light curve has a maximum minimum ratio of at least 6 to 10. That means that the body itself should have an axis ratio of at least 6 to 10. That is a lower limit because that assumes that the rotation axis is in the plane of the sky. If the rotation axis is tilted, you need an even bigger axis ratio. There are no color variations in the light curve, which suggests that it's not albedo variations. In comparison to other asteroids, you can see the spin rate is not so bad, but the amplitude of the light curve is way up at the top end of solar system asteroids. This, of course, has led to the iconic picture of what Oumuamua should look like. The next puzzle has to do with the velocity relative to the local standard of rest. So its heliocentric velocity at infinity looks like this. The standard estimate of the velocity of the local standard of rest looks like this. You can see that the velocity in the radial direction is consistent. The velocity in the vertical direction is consistent. The velocity in the azimuthal direction is not consistent, but there's considerable controversy about what that velocity actually is. And there are estimates in the literature ranging from 26 to 17 to 12, so I'm not too worried about this discrepancy. So it looks like it's moving very close to the local standard of rest, but the velocities of objects like stars or small bodies relative to the local standard of rest increase in a random walk with age as a result of kicks from giant molecular clouds. So if it's going to be so close to the local standard of rest, it must be very young, less than a gigayear. Then you have to ask what destroyed it. We know of no process that would destroy old Oumuamuas, so why are we, the first one we're seeing, young? And of course, if the lifetime is short, the problem with the mass budget is much worse. There's also a puzzle about the non-gravitational acceleration. Orbit fits suggest that the residuals in the orbit can be reduced if you add a small 1 over r squared repulsive force at the level of about 10 to the minus 3 of the sun's gravitational force. So these are the residuals with gravity only. These are the residuals including an extra force. Normally you would say this sort of non-gravitational acceleration is due to outgassing, but again, there's absolutely no evidence for outgassing, and there's no sign of a coma. Moreover, if it was outgassing at the rate required to produce this, unless the outgassing was completely symmetric, it would spin up or spin down the object on a time scale of a few weeks, which wasn't seen. Okay, so at this point, those are the main puzzles. I have to address the question of whether it could be a spaceship. The spaceship solves puzzle number 1. You know, it might be that the ship was directed towards us, and that largely solves the problem that there's not enough mass budget.
Could have just been parked at the LSR then.
Puzzle number 2, the lack of coma. Spaceships, we know that spaceships are made of metal, not ice, so that's okay. The shape, that's the estimate of the shape, and we all know what spaceships look like. The velocity close to the LSR, I think it probably doesn't naturally explain. The non-gravitational acceleration actually does pretty well on, because if it's a spaceship, it's hollow. That means the ratio of mass to surface area is far lower than a solid body. The ratio of mass to surface area or the surface density that you need is about 10 to the minus 3, 10 to the minus 4, around 10 to the minus 3, 10 to the minus 4 grams per square centimeter. Grams per cubic centimeter, which corresponds to a hollow body with a wall thickness of a few centimeters. And in fact, if you compare Oumuamua to the International Space Station in terms of total size and surface density, it's actually a pretty good fit. It doesn't explain why the colors are similar to some asteroids. They did look for radio emission. There's no radio emission. The light curve isn't due to porthole lights coming in and out of view, because the flux goes like the product of 1 over r squared from the sun and 1 over the distance squared from the Earth. So it's clearly reflected light rather than self-generated. How long do we have to wait to find another one? The Pan-STARRS near-Earth asteroid search that found it had gone on for 3.5 years. The interval since the detection is now 1.5 years, so the probability we haven't had any additional detections by now is about 70%. That's not a concern. Additional detections by 2025, the probability is the inverse. That is, there's a more than 50% chance we should see another detection by then. At about that point, we should have LSST and survey results. And so basically, The conclusion is you shouldn't think any more about Oumuamua. You should just wait for LSST. Okay, let me sum up. Try to persuade you that there is a simple model for the formation of the Oort cloud that explains most of its properties and its origin naturally, and is mostly consistent with the statistics of observed orbits. The properties of the cloud depend strongly on the configuration of the giant planets in the sun's galactic environment. So if we start talking about Oort clouds around exoplanets, we had better be cautious to recognize that they might look very different from our own Oort cloud. The properties of the members of the detached disk, such as Sedna, can be explained by the presence of bodies of Mars size or Earth size in the protoplanetary disk, and there's a significant chance that some of these are still in orbit outside the sun in a few hundred astronomical units. And we'll just have to wait and see about Oumuamua. So that's all I wanted to say, and maybe while we do questions, I'll just put up a summary of the observational constraints on Planet X that you can look at while we do the questions.
Right at the beginning, you argued that the distribution of comets was within 20 AU, suggested they came from the Kuiper belt.
20 years.
20 years?
Yes.
20 years. Okay, 20-year period. Suggested
Yes.
they came from the Kuiper belt. But later on, when you showed us the model, that Luke Jones' model of the formation of the Oort cloud, there was a concentration of comets in exactly the same part of the phase space that you showed us. And since the orbits are all time reversible, why is that? Why could we not have the comets from the Oort cloud being funneled back by the planets into the inner solar system on orbits which are not terribly inclined?
Well, so there was a population, which I called the scattered disk, of things on very high eccentricity orbits that were relatively flat. But I think what you're asking is whether comets from the Oort cloud could be funneled back into a flat configuration.
Yes, I am, and that's because the dynamics is time reversible.
Right, the dynamics is time reversible, but remember that it's a time reversible system subject to an external heat bath consisting of all the passing stars. So it's better to think of it as having a heat bath, and then once you go to a maximum entropy state in that heat bath, you can't get back to a low entropy state. Once the system is spherical, it starts off flat. As you know, Jerry, once you have a flat disk and you heat it up, it's not going to go back to being flat again.
I completely agree with you, but on that point of view, but you're not really answering the question I asked, which is the distribution of eccentricities, inclinations of these things could be set by the fact that there are comets coming in which only come near to the sun, near to the Earth, the inner solar system, because they've been deflected by the outer planets.
Yes, well, so it is true that what's happening with the short period comets is that there is kind of a billiard game going on where they get a small change in their eccentricity. They start to interact closely with Neptune. They random walk around Neptune, and then they get a perihelion that becomes small enough that it encounters Uranus, and then they random walk for a while and work their way in. And in fact, if you look at the short period comets, the ones with period less than 20 years, they're usually called Jupiter family comets. The reason for that is that their aphelia are almost always at Jupiter, and the reason is that Jupiter was the last piece of the billiard game that brought them into the sun. So yes, that.
How do we know for sure then that those comets originated in the Kuiper belt and not the Oort cloud?
Because it's a reasonable question. So I would say the answer is because simulations based on the assumption that the source is the Kuiper belt are completely sufficient to explain the flux and the orbital properties of the comets with periods less than 20 years. if you, my guess is that if you tried to explain those with the, in fact, I'm pretty sure, tried to explain that with Oort cloud comets, you couldn't possibly get enough flux without overproducing the high inclination ones.
Well, remember, Scott, you also get a long orbital distribution in the argument of perihelion.
Yes, 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 right. Okay.
So if you capture from the Oort cloud, you tend to get arguments of perihelion out of the plane at 90 or 270, whereas the actual arguments of perihelion are near 0 180.
Right. Crystal?
The sun's fallen into spiral arms, I don't know, 50, 100 times in its history. What happens to this Oort cloud from that perturbation in the, boundary conditions of potential?
Well, so basically, when you're in a spiral arm, the tidal force is stronger for a limited period. So the the loss cone shrinks. You would get a temporarily increased flux of comets from the inner Oort cloud, and then it would go back to normal once you left the spiral arm. So there have actually been proposals that that the rate of extinctions has been periodic. The rate of impact craters on the Earth has been periodic, and it has been argued that that periodicity is due to the sun passing in and out of the spiral arms. I think the original arguments that these things are periodic are maybe a little weak, and the argument that our passage in and out of the spiral arms is periodic is also a little weak. So this is worth remembering, but not worth taking too seriously. Mm-hmm.
So you said you needed a fractional amount of 10 to the minus 3 non-gravitational acceleration, right, to explain, or the Kavli
Right.
explain the orbits. But if
Well, only one orbit.
well, the one, that's
Right.
I see, but that's a time-independent term. And I'm wondering if there's some plausible ways of introducing some time dependence to that term that would account for both the lack of the coma and
I don't know of any. I think so. You could imagine that. I mean, there was such a limited observation arc that the observations looking for coma or looking for gas around it were more or less the same range of dates when they were measuring the orbit. So it would require a pretty specific time variability to turn off and turn on the gas. So it's possible that you could, but it's not obvious. Mm-hmm.
When you mentioned that when comets get close to perihelion, they get a kick, and then they can become more bounded or leave the system. Is that a mechanism for the ones that are becoming unbound to then kick another comet as they are leaving the system, and would that help with this stable but leaky state?
In principle, but in practice, the comets are only 10 to the 16th grams, and the chances of collisions between them are really very low, at least in the current solar system. So I did look at that process once, and it's very hard to make it work. Mm-hmm.
When you mentioned about this conceptual greater mass, what I'm trying to say is that when mass of greater is small, then you have a large non-linear effect, and the potential becomes recover time from larger distances. So I think that in this, accounting for this would weaken the constraints. You see, because maybe you know that technically, if you consider small mass limits, that in linear approximations, then you have 25% difference from bending of light, for example.
Mm-hmm.
And to explain why it doesn't happen with a small mass, you're accounting for this nonlinear effect, but then the potential is also different.
Yeah. So I mean, I'm not, of course you're right, I'm not really arguing that this is a serious way to say anything about the graviton mass. But I think it is a remarkable statement about something that it comes out so close to what you would expect from these very naive arguments.
Yeah, no, but I mean, numerically, you can say it's still unique.
Yes.
Accounting process.
So inspired by particle physics, when you have a standard model, the tradition is to spend a lot of money to build a very expensive bit of kit to ensure that the theory is correct. So what would be needed to image the inner Oort cloud?
Well, so first of all, I think astronomers have tried to rise to the task. There was a proposal to NASA to build a space-based mission that was going to look for occultations of stars by comets in the Oort cloud. So we have not been idle. I think the only plausible way to image the Oort cloud is maybe not so much to look at our cloud, but to go out and look at other stars. So, for instance, there have been efforts where you take the Planck data and you stack the Planck maps around around 10,000 nearby stars and see if you see any infrared excess going out to around 10 to the 3 or 10 to the 4 astronomical units that might be due to Oort clouds. But I think with current surveys, that's wasn't really expected to work so well, but it was a nice idea.
So planet X, as envisioned by the Tegan and Brown, has a semi-major axis of about 600 AU. And I think that was getting maybe a factor of a few less than the inner Oort cloud comets you said LSST could detect. Will LSST be able to provide any constraints on planet X via the number of comets it detects?
It will certainly provide some constraints. I mean, obviously, if you have a big enough planet X, it'll completely change what you think the comets are out there. But I haven't tried to think about that. Let me put it this way. I don't think it's going to convince anybody one way or the other whether it exists.
So the origin of Oumuamua, I mean, since it is near circular orbit, suppose it originated from a star, it was an Oort cloud object from another star. That kind of puts constraints on its ejection velocity has to be small, and therefore sort of the delta 1 over A from the original solar system has to be like comparable to our, Jupiter's kicks or
Yeah, I don't think that's a real problem.
I'm just saying that
it can't have got it ejected at very high speed. Yeah. Yes, I think it would be okay if it was ejected by Jupiter, but it also means that the other problem is the star would have to be young, and most of the ejection of the Oort cloud doesn't happen until gigayear timescales or later, so it is a problem.
So on that same topic for Oumuamua, all of these models of solar system migration, we have the massive planets, NEAS model, etc., they require kicking out massive amounts of more traditional rocky asteroids. Would that be a potential source for this, or would those kicks have to be too large?
No, so I think that's the default model for where Oumuamua comes from. But as I tried to indicate, you have to stretch the mass budgets by quite a bit, particularly given that only 10% of planets have, only 10% of stars seem to have giant planets that could kick things out. The sort of planets that Kepler is discovering would be hopeless at contributing to this because their escape speeds are too small, and so the generic fate of a planetesimal there is they end up colliding with the planets rather than getting ejected.
All right, I think we should thank Scott.